Hello everyone. In my recent video on dot products and vector norms, I received a really interesting question. Is a vector norm a distance measure? Why not a similarity measure? It's a great question. While exactly it is not what the questioner meant, it is true that the concepts of distance and similarity can be a bit confusing. By the end of this video, you will have a clear understanding of the difference between the two. Here on this channel, I strive to bring you lectures that range from the basics to advanced topics in data analytics. I also love engaging with your questions, so feel free to drop more in the comments. If you enjoy the content, don't forget to hit that subscribe button to stay updated. Let's dive in. In the previous video, I explained that a vector norm can be a measure of distance, while a dot product can be a measure of similarity. Let me introduce the concept of separation to understand the difference between distance and similarity. The separation between vectors can be represented primarily from two perspectives, distance perspective and angle perspective. Regarding a distance perspective, the most popular measure to quantify distance is Euclidean distance. When considering the angle between vectors, we can use the dot product to indirectly measure the separation. A large dot product indicates that the two vectors point in the same direction, while a low dot product indicates that they are moving apart. A smaller angle indicates that the two vectors are more similar. In this way, distance simply indicates the separation between two points or vectors, while similarity indicates how alike their direction and magnitude are. To make the difference between distance and similarity clearly, let's explore properties of each concept. A distance measure quantifies how far apart two points are, or two vectors are from each other. It represents a spatial separation, that is, actual physical distance in space. A distance measure possesses the following three properties. The first is non-negativity. Distance is always a zero or positive value, and negative distance does not exist. The second is symmetry. The distance from point A to point B is equal to the distance from point B to point A. The third is triangle inequality. The distance between any three points is less than or equal to the sum of the distances between the other 2 points. A similarity measure quantifies how alike 2 points or 2 vectors are. It measures how closely related their direction and magnitude or specific characteristics are. Similarity measures can take relative values, where higher values indicate greater similarity, and lower or negative values indicate dissimilarity. By definition, similarity is quantified based on direction and magnitude. Regarding direction, if the vectors point in the same direction, their similarity is high. Regarding magnitude, if the magnitudes of the vectors are similar, their similarity is also considered high. Similarity considers direction. Therefore, it can be computed for vectors, but not for points because points do not have direction. Let me explain in more detail why the dot product is a measure of similarity rather than a measure of distance. The dot product is a scalar value between two vectors, A and B. The dot product functions as a measure of similarity for the following reasons. First, the dot product considers the direction of the two vectors. Specifically, a larger dot product indicates that the two vectors point in the same direction, reflecting higher similarity. For example, when a dot product is positive, the two vectors point in the same direction, or are close to pointing in the same direction. When the dot product is 0, the two vectors are orthogonal, meaning that there is no relationship between them. That is, a lack of similarity. When the dot product is negative, it means that the two vectors point in opposite directions, that is, low similarity. In this way, the dot product is considered a measure of similarity because it reflects the orientation and the relative relationship of the vectors. Next, we want to clarify why dot product is not a measure of distance. The first reason is its non-distance nature. Distance typically represents the shortest separation between two points in physical space. But the dot product shows the relationship between two vectors. A large dot product does not necessarily mean that the two vectors are close together. The second is possibility of negative values. The dot product can take negative values, whereas distance is always a non-negative value. Thus, the information from the dot product differs from that for distance. Therefore, while the dot product's formula contains the distance between vectors, the dot product itself does not represent the distance. The norm is considered the measure of distance for the following reasons. First, the norm is always non-negative. The norm always takes a value of 0 or higher, which fulfills the property of distance. The norm of 0 indicates that the vector exists at the origin. In addition, the norm satisfies the triangle inequality. That is, for any vectors a and b and c, the following inequality holds. The reason the norm is not a measure of similarity is that the norm measures only the magnitude of a vector and does not provide information about direction. Two vectors can point in different directions and still have the same norm, but this does not mean similarity. The norm can be used as a measure of distance because it quantifies the magnitude of a vector, but it cannot be used as a measure of similarity. It is because the norm lacks direction information and cannot distinguish between vectors of the same magnitude pointing in different directions. Therefore, other methods, such as the dot product, are necessary to assess similarity. Now, we can obtain clear distinction between the concepts of distance and similarity. Thank you for watching. Please thumbs up and subscribe to my channel.